Well, it looks like it's 1 o'clock and it's time to get this show on the road. So, welcome. Welcome to City 17. It's safer here. Anybody remember that line? You should. It's from the greatest first-person shooter of all time. Anyway, this is the Tutor Wizard, and I'm your host. My name is Tim. And today is lecture number 1 in a series that's going to track with a spring semester introductory statistics course. I'm getting ahead of the game. The spring semester hasn't quite started yet, but this will get us off to a good start, and it'll be ready to go when you're ready to go. It'll be 6 weeks of fun, learning statistics. Unless it's your second or third time through, and I do feel your pain on that. I know some people have struggled a long time and have to redo the course a couple of times because it's a bit of a challenge. No way around that. I'm not going to tell you it's not a challenge, especially if mathematics is not your strong suit. But I will make a few comments about statistics at this level. So I'm going to oftentimes refer to Statistics 151 or 161, and that's local to our university here. But at the end of the day, the material in just about every non-engineering first semester statistics course is roughly the same. And we might as well take a look at what's the sameness of that. There are 3 distinct discussions. You're going to start off with descriptive statistics, and this is stuff, material, ideas that you've already seen. Charting, numerical summaries, some calculations. It's a way to describe data. Now, if you think about this for a minute, if I just throw a list of numbers at you, the average person is going to look at it and say, well, it doesn't mean anything. Now, if the numbers are sorted from smallest to largest, you may see a trend. Now, I just don't mean getting smaller or starting small and getting larger. I mean, you may see some clustering or you may see some other behavior. But it's pretty hard to do, and most people aren't going to do it. But with descriptive statistics, whether it's numerical summaries, we can tease out of the data certain characteristics that give us information. Average values, which we'll usually call the mean in this course. We can talk about how the data are spread out, usually call that variance or standard deviation quite often. If we're doing graphing, and we'll make charts. We can do histograms, which are similar to bar charts. There's some subtle differences between a histogram and a bar chart. We'll talk about that, which one's appropriate to use and when. We can do smooth curves to talk about the likelihood of a value occurring. We can do scatter plots. These things, we're going to do all these things in this course. And you'll come away with a better understanding of how to illustrate characteristics in a data set that you're working with. Because if you're in the university environment, unless you're doing something purely in the Faculty of Arts, you're probably going to run into data somewhere. So this is good skills. And even if you don't have to manipulate the data, you're highly likely to have to interpret somebody else's manipulated data. And it's good to know when you're looking at utter nonsense, because sometimes people are going to try to fool you. Ultimately, they're only fooling themselves, but at the end of the day, it's still worth a shot, at least in their mind. So there's many advantages, even just paying attention to and getting a good handle on descriptive statistics. And that's what we're largely going to get started with here in the first few lectures. Well, statistics, once we get past descriptions, is propped up by concepts from probability, chance, or luck. And you're often going to hear me talk about luck in the phrase random sampling variability. Now, we're not going to run into that right away, but just so you know, there's lots of different ways to talk about luck. And we'll beat that up in the probability section. Just as a heads up, probability may be one of the more difficult topics. Oh, we have an ad break running at the moment, so I'm just going to hold off a little bit. I know this will be a different break on the archive stream. That's fine. While the ads are running, I'm going to tell you a story. The semester just wrapped up. Final exams finished yesterday, actually. And already you hear about stories that someone got busted cheating. So the one that's currently going around is a couple of high-performing students, both of which are attempting to get into veterinarian school, who are both apparently, now this is third hand, so treat hearsay for what it is, apparently they had already passed the oral interviews, which means you're pretty much in, and they got busted cheating. Prof, who was monitoring the exam, was suspicious, challenged these two students to stand up separately. One's cell phone falls to the floor with cheat notes on it. The other one had cheat cards. They fell to the floor. And the kicker of this particular story is the prof running the exam is also sits on the board of admissions into vet school. Wow. Talk about shooting yourself in the foot. Yeah. So if you're thinking that you can outfox your prof, don't. Remember, they've been around a long time, and they were students too at one time. You're not going to be smarter than your prof. Anyway, the ad break is over. We'll get back to the main part of this. So when we talk about probability, we're really talking about chance. And directly related to chance is the behavior of random events. Randomness is all around us. We'll explore a lot of ideas in randomness, and we're not going to beat up the whole concept of randomness by getting into things like Brownian motion or deeper concepts of randomness. But it does play a role in statistics, particularly in inferential statistics, which is how we're going to wrap up the course. Inferential statistics is a topic where we begin with data that we've gathered through a process called sampling, and we're going to try to use that data to test ideas and make inferences by, that's kind of testing ideas, right? Let's see, the data seems to suggest that something may be true. Well, we're going to try and find out whether that's true or not true. I'm not going to talk too much about that right now. The point is, it's coming up, it's very interesting and very important in this course. And for you, again, maybe you don't plan on doing data analysis, but that doesn't mean you don't have to interpret somebody's academic paper. And most academic papers that are really interesting don't stop at descriptive statistics. They also discuss inferential statistics. They test things, they test hypotheses, and you need to know how to interpret that. It's not hard, it's not rocket science, you can do it. But this outlines the main topics in this course. I call them the best three topics, and there's subtopics as we go through here. But don't let that throw you. Now, some words of encouragement. If mathematics is not your forte, that you need those 3 credits in math, part of your degree, statistics is probably a pretty good course to take, in my opinion. And I'm not a rocket scientist. Yes, I'm talking about math online, but there's many, many, many people far more mathematically adept than myself. So what I guess I'm saying is if I can learn this stuff, so can you. So keep in mind, I like to tell students that this is not really a mathematics course. This is an arithmetic course. There are a couple of places in this course where we can do algebra, but that is not going to make or break this course. If this was first semester calculus, yes, algebra is fundamental, as all you do is manipulate the living daylights out of equations. Here, however, we're doing basic addition, subtraction, multiplication, and division with the occasional square root thrown in. And that's pretty much the extent of it. Plus you get a calculator that does the operations, and you get a formula sheet. So if you're going, I can't memorize formulas, you don't have to. They're going to be written down. You just know which one, what you need to know is which formula to use and when to use it. Which brings me around perhaps to the hardest part of this course. This course is a critical reading course. You need to read carefully. Most problems are posed as word problems because statistics itself is ultimately the queen, the king of word problems. But they're not all worded very well. Sometimes you get questions that are worded in a cumbersome manner, and you need to carefully read that because certain numbers represent certain quantities, and you need to know which quantity to assign to which symbol. Otherwise, you're going to get the wrong answer. So if you're going to do anything in this course, make sure you concentrate on careful reading. And I'll have some tips about that as we go through. I can't sit here and tell you all the pro tips for this right off the start because, well, I'll probably miss half of them and you'll forget the half I do tell you. And everybody's kind of different and different techniques for different type of problems, so we'll talk about it as we encounter them. But as far as the subjects of this course go, descriptive statistics is where we're going to start. This thing here is the first thing we're going to do. Probability is the second thing we're going to do, and this is roughly where the midterm pops up too, by the way. Inferential statistics is how the course will wrap up. Now, what's the hardest part of the course, in my opinion? The most abstract part of the course, and therefore the most difficult, is the concept of probability, because it's counterintuitive in many cases. Lots of people have incorrect ideas about probability. You may know someone that says, I go to the slot machine, I pick two machines, the VLTs, I guess, is what we have around here. I guess you can call them slots, but whatever. You got video lottery terminals is what they're technically called. And they will sit there and plug credits into the machine saying, I eventually have to win. Well, there's certain probability distributions that allow you to calculate what's the likelihood of ultimately winning. But for VLTs, every play is independent of any other play, and you just cannot load a machine up and say, it's ready to pay off. No, it doesn't work that way. So one of the things I like to do when I talk about probability with students is, besides applying it to other real-world situations, I also like to talk about it in terms of games of chance. So we'll talk about that as we make our way through here. We will do some simple computations today, by the way, just to test your ability to crunch numbers. And we'll talk about a couple of definitions, and we'll talk about some of the layout of the relationship between ideas, terminology, symbols that represent terminology, and how they're used. Actually, I'm kind of giving away the game. Let me just go to the next slide over here. Why statistics? I should have probably flipped to this slide earlier, because I've kind of already moved into that topic. But we use statistics, as I mentioned, to describe data. And let's face it, if you're just running a numbers system, a data collection system, you're just going to end up with a list of numbers, and you got to have some way to compare them. Oftentimes in quality control, you're going to get a list of measurements from one day's production run, and then you're going to get a new list from another day's production run. Well, how do you know if they're the same, reasonably the same, or maybe the machinery is requiring calibration? Well, just to stare at the numbers isn't going to tell you, so describing data is useful for that. Calculation of chance, well, we just talked about the video lottery terminal thing. We will talk about some of these things. Casino games in particular are great subjects for that. The ability to make predictions in the sciences, by the way. Let's say you're doing research and you think you found the next greatest thing since sliced bread. How do you know it's actually legitimate? Guess what? You do a statistical analysis. Oftentimes in statistics, the application of statistics to, say, physics, you don't really want to write a paper saying that you found the next greatest thing until you can suggest that your discovery is extremely unlikely to have been a random event. And the way we measure that is in terms of sigmas. That's this little symbol here. This is the Greek letter sigma, the lowercase one. It represents a standard deviation, so 6 standard deviations away from what you expect the average outcome of your experiment to be. Now you can start talking about, oh, hey, I found something noteworthy. And 6 sigma is quite a bit larger than 1 in a million. It's about 1 in 10 million. I have my calculator here. I can actually do that. I'll tell you if we're using the standard normal distribution, which is phrases that we're going to explain as we get through it. So if I'm 6 standard deviations away from the average, like I said, that is a very, very large number. Or actually, it's a very small number, but it's 1 over a very large number, okay? So if I have that, and the upper bound is that, if I set the lower bound to that, this works out to, call it 9 times 10 to the negative 10th power. So many zeros before the first non-zero digit. So that's how rigorous experimentation in science has to be. We also mentioned testing hypothesis, which kind of goes hand in hand with the making of predictions. This will wrap the course up with. We'll just save a discussion for that for another time. Actually, no, let me illustrate an example of that. The hypothesis that smoking cigarettes leads to lung cancer as a consequence of smoking cigarettes. For many decades, that was an argued hypothesis. It was easy to say that yes, there seems to be a correlation between people who smoke, and we're going back over 100 years here in this discussion, so the smoking of tobacco in its various forms, and oral and throat, lung cancer, etc. The correlation was always there, but it was easy to dispute causality. Does it cause cancer? It took many decades of research, carefully controlled experiments to make that hypothesis bulletproof. A lot of money was spent by the tobacco companies to dispute outcomes. It took carefully controlled experiments, repeated experiments of many, many types to actually turn that hypothesis into something that you can say, we've proven this. It's very hard to prove things, Statistics doesn't guarantee anything to be correct. In statistics, there's always room for error. We try to never say, this is exactly the reason for that outcome. If you're going to do things like that, always remember how difficult the tobacco leads to cancer relationship was to finally settle arguments there. And some people still argue about it today, but you'd be hard-pressed to find anybody with credentials that would say, well, it's just a coincidence that the smoking of tobacco products in their various forms leads to cancer. It's pretty much settled, but it wasn't easy. It took a long time. But as a general practitioner in statistics, if that's how you end up finding your way through university, beware of anybody saying, well, statistics proves this. Right there, you go, what? You sure you know what you're talking about? Anyway, let's move on. Language and terminology. So you already heard some of the language. We're going to get into some of the terminology. I like to get this straightened out right away because oftentimes it's not made clear to students in the first few uh, lectures about how this works. So let's take a look at what I've already got set up here. I'm going to try the laser pointer today. Oh, that's not the laser pointer. Let's try this. I haven't really explored. I'm using Open Board here. That's the software package. It has a lot of interesting things. I haven't fully explored it. What do we do? Why do we do statistics? Well, here's why. Let's talk about Canada. Well, that's where this stream is originating from. If I want to understand characteristics about the population of our country, the best thing I could do is conduct a census. Census, there's one of the words. Census means you measure everybody. You talk to everybody. But even census, censi, okay, Teenage Mutant Ninja Turtles just popped in my head there. Sorry, that's a tangential. I like to go off on tangents. I'm trying really hard today to not do that. So the thing about census is it takes a long time to measure, talk to everybody in the country. And by the time you're done, you spent a lot of money, you spent a lot of time. No doubt mistakes have been made. Some of the people you talked to or interviewed at the start of the census are now dead. Other ones have been born. So even with a census, you still don't get complete information about your population. This thing here is what you're trying to understand. This is how governments decide what they should do, when they should do it, how much money to put into some program, because it's based on populations. So the way this works, and there are certain aspects to correct sampling, and we'll talk about them in another lecture, but we do samples. These guys right here. If I collect a subset from the population, which we're going to call a sample, the subset will accurately estimate the population. This is how you can talk to 3,000 people across the country and extrapolate from there conclusions that are very accurate about the characteristics that you're interested in that are found throughout the entire population. Again, language and terminology, we would have to have a representative sample. Not easy to get. Let me illustrate the idea of a representative sample. Let's talk about campus life. Here in Canada, specifically at the university that I work at, about 60% of the students are female, 40% are male. Well, that means if you were to collect a sample of 100 students, you would want to have very close to those proportions so that they would be representative. So a collection of 100 people randomly chosen, and let's say I had 65 females and 35 males. That's pretty close, nothing wrong with that. But if I end up with 90 males and 10 females, that is not a representative sample of the population. And that means any inferences, anything that I try to learn from that sample about the population will be biased. There's another term. What's a bias? I just told you what the bias is. The bias is when the sample doesn't represent the population. We'll talk more about that at another time when we get into sampling. So the first thing to remember then in the practice of statistics is that samples estimate populations. Easy enough? I think so. We should highlight that. I'm going to try my highlighter here. How big's that one? Ooh, it's a big one. All right. Now, whoa, what happened there? Oops. You know what? I hit the eraser button. How silly. Trying again. There we go. There we go. Okay, why is that still doing that? Oh, software is hard to use when you get old and stupid, you know. Trust me on that. Okay, so there we are. And I want a line width. That's why. There we go. Ah ha 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 ha. Okay, there we go. So What do we know? What have we learned here in this discussion? Samples estimate populations. That's the first thing you want to keep in your mind. Throughout this entire course, if I want to know something about a population, I have to study a sample. Now, what do we call the numbers, the data? A sample produces statistics. So if I talk to 100 people and I find out the average age is 35, that's a statistic. Now, what do I do with a statistic? A statistic is used to estimate a parameter. Now, the parameter is the characteristic that associates with populations. So just like up here, I'm going to turn over here to this one now. So just like on the top row here where I use a sample to estimate a population, then I would use a statistic to estimate a parameter. The statistic comes from the sample and the parameter speaks to the population. That's the relationship between words and ideas. So when your prof is talking about a statistic, then that is something that's been computed from the sample. And the sample is used to provide an estimate for a population. So statistics estimate parameters. Parameters are associated with populations. Fundamental idea right there. Now, we have a number of things that you can see on the lower part of the screen, so why don't we just pull that up a little bit. Now, these are common statistics and parameters that we're going to encounter in this course. Now, you're used to the word average. Most people, I think, know how to compute an average. Just add up all the numbers, divide by how many. Well, in this course, we call those the means. It gets a bit cumbersome when the word mean also refers to understanding. So if I'm talking about the mean, which is the average, I can ask you if you know what I mean about the mean being the mean. You can see how this turns into a Three Stooges episode. And if you don't know who the Three Stooges are, go to YouTube and look it up. Anyway, sorry. I'm old, okay? I'm allowed to make references like that. Now, symbology. Typically, in this course, at this school, the measured statistic for mean symbol is Y bar. Some places are still using X bar. It doesn't matter. The point is they represent the average value. You got textbooks too, right? If the textbook is using X bar, then the prof's probably going to talk about X bar. Most of the current textbooks use Y bar, so that's why it's kind of shifted over. It does not matter. Now, these symbols provide a lovely estimate. Did I pronounce that right? An estimate? No, it's an estimate. That's like in Canada, we have the city of Toronto. But if you look at it, Toronto, well, very few people ever pronounce that way. It's Toronto. That's how we say it in the West, or Toronto, or Toronto. Even here in Edmonton, when you listen carefully, Edmonton, you can hear an I in there. There's no I in the word Edmonton, but we pronounce it that way. It's got nothing to do with statistics. It's just an observation in life. Okay, so what is this? Our statistic Y bar provides an estimate of the Greek letter mu. So that's a stylized U. Some people write it as a stylized M. I'm not entirely sure where the truth lies on that. But the pronunciation is mu, or moo. I don't care. Knock yourself out. Do it any way you want. Mu or moo. So, Y bar is a statistic, mu is a parameter, and Y bar provides an estimate of the parameter. And by extension of our ideas, then, it also provides an estimate of the population average. So the sample average estimates the population average, and as we'll see later, it's very, very accurate. Oh, hey, we got somebody on chat. What's going on here? Where's my glasses? It's e to the 2 pi. Well, hello, e to the 2 pi. You know, if that was e to the negative pi squared, you would fit right in, because then you would be the integrand in our, well, almost the integrand for our standard normal distribution. Anyway, carrying on. Welcome, by the way. Nice to have you with us today. So, one of the things that we, again, more terminology, the mean is an estimate of where the center of the distribution, there's another term, of our data lies. But we also want to know how our data is spread out. And that can be measured with variance and standard deviation. A little bit of math involved. I'm going to show you today how to compute these three statistics before we wrap this lecture up. So variance of a sample is s squared. Typically it's lowercase s, and it provides an estimate of lowercase sigma squared. There we go. Now, there are some computations in this course where we will work with s squared, or variance, but for the most part we want standard deviation, which is just lowercase s. In other words, it's the square root of variance. So s, standard deviation then, estimates lowercase sigma. Easy as that. Now, a couple other ones here. There's going to be a few more we'll run into as the course progresses, but I don't want to throw too much at you all at once, because, you know, the brain will only process so much information. So if we're talking about purely numerical data, you can calculate mean values, you can get the variance, you can get the standard deviation, but sometimes what we have is categorical data, or nominal data, if you want to talk about it in that context. Categories, you know, so it's red, blue, alive, or dead. Nominal could be, well, the root word in nominal is nom, which means name, so anything that's named data, we can usually turn into percentages. Let's think about the alive and the dead. Say you're in charge of keeping the fish alive in some biology lab. You know, oftentimes they work with zebrafish. Well, if something goes wrong with the feeding system or the filtration system, you might come in, the tank might have had 200 zebrafish, but now there's only 30 alive. So what's the percentage? Well, alive and dead, there's your categories. And if I got 30 out of 200, so my proportion is 15%, or 0.15. So we label that as lowercase p with a hat on it. So p hat is the proportion symbol for a statistic of that type, and is used to estimate lowercase p, or oftentimes as a little p with a subscript 0, p null. Easy enough. That's coming up. We'll talk about that in more detail as we progress. Correlation is a topic that leads to regression, but correlation talks about the association between two variables, and that has lowercase r. We're not going to talk about that too much right now because that's later on in the course, but correlation, if two variables are related to each other, we can attach a value to that that will illustrate how strong that relationship is. And that has a lower symbol from Greek letters again of rho. That's not a P, by the way. That's a stylized, well, it does look like a P. I'm not going to kid anybody about that, but it's pronounced row, as in row your boat. So that, again, correlation from a sample is going to provide an estimate for the correlation of the population. And this is part of regression analysis, which is going to be in the course. Simple linear regression in this course. Multiple linear comes in the second course. This is y hat, and it provides an estimate for y. So there's some introductory symbology that you need to know or be conversant with. But the most important thing I want to recap on this slide is this relationship. If you take nothing away from this chit-chat right now, the stuff I have highlighted in green here is, you need to know that. Oh, we got another ad break. So we'll chat a little bit about life in general as the ad break rolls on. Samples provide estimates of populations, and the numericals that go along with that then are the statistics from the samples for the parameters which talk to the populations. And if you get that down pat, you're already on your way to a successful course. All right, what do we got going on here? Got a couple more ads. Yeah, I got one left to go here. 1.5. This one's almost done. Okay, it's a Canada ad. No problem with that. Thank you. Red Bull, it gives you wings. And we're back. Okay, so I did want to point one last little thing out here. I meant to do it earlier and I got busy yakking about something else. You'll notice how do you remember this, right? Well, sample starts with S, so does statistic. And parameter starts with P, and so does population. So there's a mnemonic on which word is associated with which concept. Okay, enough of that slide. Let's keep going here. So we're going to look at some basic calculations today just to illustrate how easy this course can be. Remember, you get to use a calculator, right? Doesn't have to be brutally hard. And make a note here. If I look over here, S, this is sample standard deviation, not population. We're going to talk about that in a minute. But the point is, this nasty little square root here is probably maybe not the absolute worst computation in this course, but it might be the second worst computation. And if you can handle this one, you can handle just about everything else. So these formulas are, as with all math formulas, simply shorthand for sentences. I like to say that mathematicians are notoriously lazy creatures, because in no circumstance will a mathematician use a word where a symbol can be used to describe something, and they certainly aren't going to give you a paragraph or a couple of sentences if they can knock it all down into a simple formula. And I don't mean that in a disrespectful way. I mean, that's just how math people work. Plus, it's also a universal language, so there is that. So if this isn't the mean value formula right here, this says, recall from high school, the sum of, so that stylized jaggy E is capital sigma. The lower bound is the indexing variable I, starts at 1, and finishes at however many there are. N is where you stop counting. So what are we counting? We're counting the observations, and this is Y subscript to I. So just so you know, anything that's got a subscript, so Y, and if I put a 2 down here in the lower right, that's a subscript that would say to me that whatever that value is was the second value in a list of other values. If it was a 3, then it would be the third value in the list. If it was N, then it would be the last value in the list. Don't overthink this. So what you have to do is you compute the numerator first. In other words, you add up the observations, and then you divide by N. See? All that explanation just boiled down to that simple formula. Same thing over here with S, the sample standard deviation. Again, we have the summation formula. I is equal to 1 to N. And what we're going to do here is we're going to take each individual observation. I'm going to subtract the calculated average, some of which will be positive, some of which will be negative, and then I'm going to square it. And then I'm going to divide by N minus 1. And then I'm going to take the square root. In that order. There's also hints here on how to do this. So I'm going to illustrate this. And then later on I'm going to talk about degrees of freedom. Typically at the start of the course, degrees of freedom is not a topic that gets talked about a lot, but the course is going to gradually involve formulas that do talk about degrees of freedom. And it seems like that's a perfectly good place to talk about it. And we can also talk maybe a little bit about weighted averages. We'll see how the clock treats us here on this lecture series. So I've got something ready to go. Let's go there. Here's some data. I want to compute the mean value first. So using my formula then, I need the sum of from I is equal to 1, and there are 4 observations, to 4 of y sub I. Well, that means this can be called y sub 1, this is y sub 2, this is y sub 3, and this is y sub 4. And then we're going to divide by n, which is 4. So how does this expand? Well, this is how you do this. I'm going to drag this out because, not to be disrespectful, but simply because I want you to see this. I'm not going to make the assumption that this is easy for everyone. So I'm going to do this. Well, there's the sum. That's what the numerator is, and since there's 4 of these creatures, I'm going to divide by 4. Now, because n is 4, right? Here's n is equal to 4. Okay, so y1 was 8, and then I have 10, and then I have 12, then I have 18, I'm going to divide by 4. Well, remember your bed mass. Let's add that stuff up first. So 18 and 18 is 36. This is 48, and divided by 4. So we know that y bar then is 12. There we go. That's our average value. Now there's a concept called the weighted mean. I'm going to talk about that perhaps at another time. I was thinking about putting it in here at the same time, but I think we'll hold off on that till we need to talk about it. Means are almost always dead simple. They are what you just saw here. They can become a tad more complicated when we have different sample sizes. What's the average of 3 different sample sizes? Well, we'll get to that at another time. Not that far down the road, but we'll talk about that at another time. All right, we know that y bar is 12. Let's go to the next slide, because remember, we need that to calculate the variance and the standard deviation. And again, we're going to do sample. And I will tell you why I'm being particular about that in just a moment. So we have I is equal to 1, goes to 4. We have y sub I minus y bar squared n minus 1. Now this n minus 1 is degrees of freedom. I'll try to explain that in a minute or two. But there are 2 ways to compute variance and standard deviation. There can be the one we're doing here, which relates to the sample. So there's also the population. If I was to compute the population variance, or standard deviation, I wouldn't divide by n minus 1, I'd be dividing by n. Now the only time we can do that, or should do that, is when I tell you that these 4 numbers are all there are. This is the entire population of numbers. Then I can divide by n, divide by 4. But this data, and nearly everything in this course, relates to sample data. This is a subset of a larger group of numbers. Then we divide by n minus 1. All right, enough of that. We know that y bar, I'll repeatedly come back to that concept as we go through this course. So let's do this, and I'm going to do it in the same manner as we did on the other slide. Here we have s is equal to. Now I'm not going to write the square root right now. I simply want to expand this. So this is going to be the sum of from I is equal to 1 to 4. Now what do we have? We have this computation. There's something interesting about this too, by the way. So that means, let me write this out this way. I wasn't going to do it, but then I started doing it. So we're going to do this subcomputation first. So this is going to be 8, which is our first value. Remember, this is y1, this is y2, this is y3, this is y4. Okay, so 8 minus 12, which will square. Then we move over here to y2, which is 10 minus 12. We'll square that. Then we're going to add 12 minus 12. We're going to get lucky on that one. Square that. And then we'll come down here, and we have 18 minus 12. We'll square that. Now, I want to point something out right now. difference between 8 and 12 is negative 4. Okay? Here's 10 minus 12. That is negative 2. Just ignore the square. I'm putting the squares on because I need to, but I want you to ignore that for now. This is 0. And then we have 6. All right. If we didn't square this, each of these quantities, the variances, or specifically the deviations, would sum to 0. You know, this is negative 4. Here's negative 2. That's negative 6. Here's positive 6. At this point, if there was no squaring, these would sum to 0. And what's the point of trying to do math with 0? Because if you add it to something, it changes nothing. If you subtract it, it changes nothing. If you multiply it, everything is 0. And if you divide by 0, I'm going to throw well, I'm not going to throw anything at you, but someone will throw. Well, the universe will explode. Heat death, right? All right, so this is one of the reasons we square it. Gets rid of the zeros. If it doesn't add to 0, by the way, at that point in time, you know you've done something wrong with the average, or you've written something down wrong. So the sum of the unsquared deviations is always 0. Dandy midterm question. There's your first hint for the midterm. The sum of unsquared deviations is always 0. The sum of the squared deviations is always as small as it possibly can be. Keep that in mind. So here's negative 4 squared, so this is 16. 2 squared is 4. 0 is 0. And 6 squared is 36. So what does this add up to? 36 and 4 is 40, and 16 is 56. Okay. So now what do we have? We have S. Let's get myself some room to work here. Okay, so S, there we go, is equal to 56. Now we have to divide by n minus 1, right? So we're going to divide by 3. And then we need the square root. So 56 divided by 3, unfortunately, is not a nice number. What would it be? Well, if it was 54, it would be better, because then it would be 18. And I don't know what the square root of 18 is off the top of my head, but it should be, well, 18. So that's 9, 3, 2, 3.4. Let's just use my calculator. Not feeling it today. Sometimes I can do that stuff in my head, but not today. 56 divided by 3 is that. What is that, by the way? You're probably saying, well, don't tell me that. Just tell me what it is. 56 divided by 3 is 18 and 2/3. So 18.6666, repeating. Now we want the square root of that, so that's got to be just a little bit more than 4. I'm going to predict 4.4. It's actually 4.32. All right, so 4.32. And that is our standard deviation. Our variance, should have did this earlier, is the 18.67. Just use the 2 decimal points. So standard deviation, when you square it, gives you variance. Or, conversely, if you have variance and you take its square root, you get the standard deviation. So about 3/4 of the time in this course, maybe a little bit more, we're going to work with standard deviation instead of variance, but variance does show up here and there and is used to give an estimate of how widely spread the data are. And you may be saying, well, what do you mean by this spread business? Well, before we talk about it specifically, the mean is one of a couple of ways to find out where the center of your data happens to be. Now, how far the data extends larger and how far the data extends smaller than the mean value is illustrated by variance or standard deviation. Clearly, variance is too big. I mean, let's look at the numbers up here. The average distance between those numbers, distance here is 2, distance here is 2. Whoops. Distance here is 2 units, this is 2 units, and this is 6 units. So we got to have a number bigger than 2 and smaller than 6, which happens to be 4.32. So we'll talk more about that at a more appropriate time, not too far in the future. How are we doing on the clock here? Oh, we're right on time. I usually have this timed out for a 50-minute class, and we're 49 minutes in, and I've been deliberately taking my time with this. So what the heck is degrees of freedom? Well, I suppose we can say it's how many ways you can have numbers that give you the same answer. That's the way I'm going to approach it this. But freedom to choose. No one's going to ask you about this on an exam, but I like to talk about it simply because I'd rather have we all understand what we're talking about. Now let's say I'm going to do the, how do I want us to talk about this? In most cases in this course, the degrees of freedom for most computations is the number of observations minus 1. Not always. It can be other values depending on a number of things, but for us it's n minus 1. Now, let's say I know that y bar is equal to 10, and that 10 is the sum of 4 observations. y2, y sub 3, y sub 4, and of course we have to divide by 4. Now, degrees of freedom is going to be 3. Let me show you how that I get that. Well, we need to simplify this first off, so let's multiply the 4 from the denominator across to the left-hand side. So 4 times 10 is now 40. So what I'm getting at is I can choose, I am free to choose any 4 numbers, y1, y2, y3, and y4. If they add to 40, the average will be 10. Easy enough. Now let's let y sub 1, and it doesn't matter which y you choose. I guess I got an I there, it doesn't matter. Y sub 1 will be 15. Okay, let's rewrite this. So now we have 40 is equal to 15 plus y sub 2, y sub 3, and y sub 4. Which of course we can simplify that by moving the 15 to the left-hand side. So now we have 25 is equal to y sub 2, y sub 3, and y sub 4. Again, now I'm free to choose any 3 numbers that add to 25, along with the 15 I had earlier, and I'll still get an average of 10. Now, let's let y sub 4, just to show you that it doesn't matter where we assign these. Let's say y sub 4 is 10. All right, we repeat our process. Let me move this up a little bit. That'll do. So now I got 25 is equal to y sub 2 plus y sub 3 plus 10. And of course we want to move all the numbers to one side, so we'll subtract 10 from both sides, and now we have 15 on the left-hand side, y sub 2 plus y sub 3 on the right. Again, any 2 numbers that make 15 along with our previous choices, remember here we'll still get the average of 10. And let's say y sub 2 is equal to 8. Okay, you can probably see where this is going, I would hope. Now, here's, whoops, go back up there, thank you. 15 is equal to 8 plus y3. Oh, but now, if I move that over, now I've got this. I don't get to choose y sub 3. My 3 previous choices of y1 of 15, y4 of 10, y2 of 8, I was free to choose those, but once I've done that, the last value is fixed, predetermined by my previous selections. Y sub 3 here is 7. So this is the first degree of freedom, this is the second degree of freedom, this is the third degree of freedom, which is why the degrees of freedom, whoops, keep forgetting to put that back. There we go. Okay. That's really annoying. There we go. This is why I'm going to make a dramatic circle. Degrees of freedom here, n minus 1 is equal to 3. I was free to choose 3 values, but by doing that, the last value is chosen for me, or I could say I chose it by specifying the previous numbers. So that's degrees of freedom. No one's going to ask you to explain that on an exam. But everybody should understand that, because you're going to run into degrees of freedom in many disciplines, and I'm pretty sure that nearly every prof is going to assume you have a clue. And that brings us to the end. Let's talk about what's coming up next time. More definitions. My R's always look like V's. There we go. So there'll be more definitions. We've already talked about some of them. And then we're going to have a bit of a discussion on sampling methods as well. That'll be next time I do another statistics lecture. Won't be that. It'll be a few days from now. On the Tutor Wizard channel. Now, how about a little bit of channel business here? Channel business. End of the month is coming up. We're giving away books to supporters of our Twitch stream channel and our YouTube and our Patreon channels. If you're a subscriber, I'm going to make a random draw on the 30th, the end of the month, and I'm going to give away a number of books. Those books are listed on our Discord. There's pictures of them. A couple of Serge Lang higher-end mathematics books that are in really good shape. Got a couple of books that you may find interesting from the how do mathematicians think about things kind of aspect. Head on over to our Discord and take a look in the general stream commentary, and you'll see pictures along with a bunch of memes. And if you are willing to support us, I am willing to throw a book your way. I'll cover the shipping too on that, by the way. And it'll be a random draw. I'll pull the first name out. First name gets their choice of the book. Second name gets their choice of what's left, all the way down until they're all gone. And I will say thank you very much. We're trying to keep this stream running. Intercession or spring and summer school is always a hard time for people who make a living doing what I do and what Adrian does and what Lorenzo does. There's three of us on this. Today it's just me. Lorenzo's in the background. I know he was listening in earlier. We're trying to turn this into essentially an online undergrad education for mathematics. Adrian covers calculus, differential equations, number theory. That man's a walking, well, I was going to say he's a walking, well, it's true, he's got a PhD in math, but he's a walking ball of energy, and if you ever want to emulate someone as a mathematician, you'd be well advised to take a look at the amount of enthusiasm that that man can generate for topics. You don't have to be afraid of math. Math can be very fun. Listen, I'm going to wrap it up here. I appreciate you joining us today. There are more lectures coming. Remember, the spring school for us at this university runs over 6 weeks, which is usually Monday through Thursday for several hours a day. I'm going to try and have lectures to support that, and wish you the best of luck for that. Thank you for paying attention today, and we will catch you on the next statistics stream in a few days. Bye now.